This is Algebra 2, Lesson 8.5, Permutations and Probability. So the counting principle is going to allow us to count really big numbers. And to do that, we look at the number of possibilities to do something, and we're going to multiply it by the number of possibilities to do another thing, and the number of possibilities to do another thing, and so on and so on and so on. So this is kind of like that multiplication rule for probability of A and B. If we want the chance that this is going to happen, and this, and this, and this, and this, we would multiply all those together. Factorial is a way that we can represent multiplying a whole bunch of numbers that fit a specific pattern. And that is if I have a number and I want to times it by the next lower number and the next lower number and the next and the next and the next and the next, all the way until 1. So what that would look like would be maybe 4 factorial would be 4 times 3 times 2 times 1. Or like 100 factorial would be 100 times 99 times 98 times 97 times all the way to 1. So whatever number you have times the next and the next and the next and the next and the next as we count down all the way to 1. And one more formula would be permutation. That looks like a smallish n, a normal p, and then a smallish r. So those are subscripts, a little n, a normal p, a little r. And the formula looks like n factorial divided by n minus r factorial. But I feel like it's much easier to look at permutations as what you're doing with the numbers than it is to use that formula. So the first thing is what you're starting with, and the second thing is how many. And so what I mean is, and I want to look down really quick because I don't want to use one of these down here. So let's go 12. Sure, 12. Let's go 12 P4. So I have a little 12, a normal P, and then a little 4. What that means is start with 12, and we will count down so that we have 4 numbers. But we always count down, just like we did with the factorial. So that's 12 times 11 times 10 times 9. If I had 100 P2, that would be 100 times 99. The first number tells us where to start. We're always going to count down as we multiply until we have the number of numbers indicated by the R, by the number in the second position of the permutation. So with some formulas out of the way, let's try some examples. Example A says, suppose a license plate has any 3 letters followed by any 3 numbers. How many different license plates are possible? So we are looking at the counting principle for this. I can have any letter, any letter, any letter, any number, any number, any number. So I can say, pick a letter, any letter. What I want to know is how many letters do you have to choose from? So if you can pick any letter from A through Z, that means you can choose from 26. There are 26 possibilities for that space. Again, pick any letter, A through Z. I'm not asking you to actually pick a letter. I'm asking you how many possibilities are there. Again, there are 26 possibilities. And a third letter would be another 26. Now we're going to change gears to numbers. Any number. Pick a number. And I should clarify that this is a digit. Pick any digit, right? Because you're not going to have 42.7. That's a number, but you're not going to have 42.7 on a license plate. Usually it would be the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I'm looking at the digits 0 through 9, there are 10 possibilities. People are always tempted to say 9, but counting 0, that makes 10 digits, 10 single-digit numbers between 0 and 9. So again, pick any number from 0 to 9. There are 10 possibilities. Pick any number from 0 to 9. there are 10 possibilities. So my counting principle is saying if I want to know how many possibilities are all together, I can multiply all of these together. So that looks like 26 times 26 times 26 times 10 times 10 times 10. There are 17,576,000 possible license plates that fit this format. So if you think about the state of Minnesota, Minnesota does 3 letters, 3 numbers, but you could also have 3 numbers, 3 letters. So you'd have to double this, but then Minnesota also has vanity plates, like you can put your name on your license plate. We have critical habitat plates, so you can get like the little deer or the little loon on your license plate. We have veterans plates. We have lots of different license plates. So there's probably well over 30 million possible license plates just in the state of Minnesota. What's the probability that the license plate has no repeated letters or numbers? So this is where that counting down thing comes into play. 3 letters, 3 numbers. The first space says pick any letter from A through Z. There are still 26 possibilities. So whatever letter you pick, I'm going to just say I picked A because it makes it easy. For my second space, because I'm not allowed to repeat, now I can only pick from B through Z. And so picking A was arbitrary. I could have picked C, I could have picked F, I could have picked G, but any letter I pick takes one of my possibilities away, so now there's only 25 remaining. And now let's say I pick the letter B just to make this simple. I can now pick any letter from C through Z because I'm not allowed to reuse the A, I'm not allowed to reuse the B, and it doesn't matter if I picked A or B or C or G or Q or R. It's going to take one of my possibilities away, so I'm counting down. We just represented 26P3. We started with 26, and we put in 3 numbers, counting down 26, 25, 24. The same situation is going to happen with our numbers. If I can pick any number from 0 to 9, that means I have 10 possibilities. Let's say I pick 0 just to make it easy, so I no longer have 0 as an option. Now from 1 through 9, there are only 9 possibilities. And just to make it easy, let's say I picked 1. I can't repeat, I can't reuse the 0, I can't reuse the 1. So choosing from 2 through 9, now there are only 8 possibilities. So we just represented 10P3. We started with 10, and we permutated with 3 values, 10, 9, 8. And if I want the number of license plates that don't allow repeats, I can just multiply all of those guys. 26 times 25 times 24 times 10 times 9 times 8. And we have about 11 million license plates. 11,232. 11,232 looks good. So that means about 6 million of our license plates have some repeated digits or letters on them. 11,232,000 do not allow for any repeating values. Example B, 7 flute players are performing in an ensemble. How many possible arrangements are there for the players' names in the program? So I have 7 people. I want to place all 7 of those people in the program. That is the same as 7 factorial. So that would be 7 times 6 times 5 times 4, 3, 2, 1. I'm starting with 7 and I'm placing all 7. That's why I count on all the way to 1. Some calculators have a factorial button. I believe this one does. 7, 6, 5, 4, 3, 2, 1 is 5,040. I could have hit 7 factorial and got the same answer, 5,040. But if you don't have that factorial button, if you don't have that exclamation point button, obviously just multiply all the way, and that would be 5,040. Letter B says, if the names of all 7 players are listed in a random order, what is the probability that they are in alphabetical order? So if you, let's make this easier. Let's just talk about 3 things. If I have 3 things, and I want to put all 3 of those things down. B, C, A, B, A, C, C, A, B. Why do you have to slide so much? And CB8 would be my last one. So I have only 6 possible ways to arrange 3 things. C, B, A. 1, 2, 3, 4, 5, 6. And if I did 3 times 2 times 1, I would see that I have 6 possible ways to arrange 3 things. And I asked you how many of these things are in alphabetical order. So the first one is ABC. That's alphabetical order. Out of order, out of order, out of order, out of order, out of order. And with only arranging 3 things, we can see 1 out of the 6 are in order. And it's actually going to be the same with when I have 7 things. There are 5,040 ways to arrange the letters A, B, C, D, E, F, G. But only one of those ways is going to be A through G. The other 5,039 ways are all going to be some random scramble of that. So only 1 out of the 5,040 are in alphabetical order. Letter C. Jean-Pierre has a solo and would like his name listed first. What is the probability he will be first? So that means out of our 1, 2, 3, 4, 5, 6, 7 spaces, we aren't looking at that space because JP, he's already there, right? So instead we have 6 spaces remaining to arrange our other 6 flute players. We could do 6p6, we could do 6 factorial, we can multiply it out. 6, 5, 4, 3, 2, 1. 720. And letter D, how many possible seating arrangements are there if there is a bench with room for only 4 to sit? So I have 7 flute players, but I only have places for 4 of them. That would be 7 times 6 times 5 times 4. So we started with 7, and we counted down till we had 1, 2, 3, 4 numbers. Ending in 4 is just a coincidence. We have 4 numbers, and then we would multiply those out. 7, 6, 5, 4. And we can arrange those 4 of 7 in 840 possible ways. That's a lot of ways. We done. Good luck on the exercises. This is the last lesson of notes from the packet. So you should be able to take your final chapter assessment as soon as you have these done. Please let me know if you have any questions.